All right, and we're going to be continuing our discussion today, building some of our vocabulary around polymers that we're going to be using for the rest of the semester. So, whoops. So we're going to continue talking about the ways that polymers are connected, sort of classification schemes for polymers, and how we can actually predict the properties of a polymer on the bulk scale by looking at the molecular structure, predicting the crystallinity of a polymer specifically by looking at its molecular structure and connectivity. So before we get started into the new stuff, I wanted to review a little bit. And this is not it is a class participation activity, but it's not one that you need to turn into Canvas. I'd like you to sort of remember what the responses of a viscoelastic material are like. So draw two plots just in your own notes. Don't need to share it with anyone unless you want to. Draw a strain versus time plot for a viscoelastic material when you apply a step or a constant stress, and then release it. And then draw a stress versus time plot when you apply a constant strain. We'll give you about 1 minute to work on that. Okay, hopefully you've had a chance to draw these two plots. So these two plots are illustrating two different terms that we associate with viscoelastic materials, or two different phenomena, I should say. The first is creep. So when you apply a step stress or step force to a viscoelastic material, you get the phenomenon called creep. Can someone give me a definition for what creep is?
A strain response to unit step stress.
Yeah, but what would you see in the material? If a material undergoes creep, what is actually happening to that material? And what could you observe?
The material is deforming, right?
Yeah, it continues to deform. It deforms even when you keep a constant stress applied to it. It will continue to deform. Whereas a material that doesn't undergo creep, it will not continue to deform if you don't change the stress level. You have to keep increasing the stress level to keep deformation occurring. So that's creep. That's the first bullet point, the strain versus time response. And then the other phenomenon is called stress relaxation. So when you apply a constant strain to the material, you deform it quickly and then maintain that same level of strain. The stress in the material changes with time. So let's go to the next slide. These drawn here. Whoops, getting ahead of myself. Okay, so creep is illustrated in the first image here. Oh no, I may not have annotations. I'm trying to solve my Zoom problems, so I am doing Zoom from my browser, and it appears I don't have the ability to do annotations now, sadly. Okay, well, we'll carry on. Okay, so the first plot over here is showing the phenomenon of creep. So if we have a constant stress applied, so the stress, oh goody, I can draw. Okay, so if we're applying a constant stress with time, here's our stress. First, there's no stress, then we apply a step stress, and then we release it. So we would apply the stress here. And then over here, if we look at the strain response, the material will deform quickly when we apply the stress, and then it will deform less quickly over time, although it's still deforming until the point that we release stress. When we release stress right here, the material will slowly go back to closer to its original dimensions. Well, quickly at first and then slowing down. It may or may not fully recover its original dimensions. So it looks like here, there's a little bit of plastic deformation where the material didn't fully recover. So viscoelastic materials can have a completely elastic recovery, or there can be a little bit of plastic deformation that occurs. So that's the phenomenon of creep over here. And then over here, we're illustrating a phenomenon called stress relaxation. So in stress relaxation, the way that we do take a measurement on that, we would apply a step strain. So it's sort of like if you take silly putty in your hand and you stretch it out to a certain length, like 12 inches or 6 inches or something like that. And you were able to measure the stress of the force inside that silly putty over time. Actually, I shouldn't have drawn the plot this way because of the way this plot is. It should look like this. You apply a constant strain over time, and the stress in the material is going to decrease over time. So what's happening in a polymer when the stress is decreasing over time? Well, we know that polymers are flexible. We can get rotation around the carbon-carbon bond. The pendant groups on the backbone of a polymer can also spin around. We're going to be talking about that a lot more today. And so the physical manifestation of that, or the macro scale observable manifestation of that, is a decrease in the stress in the polymer. So when we see this stress drop off, you can think about what's happening inside the polymer. All those polymer chains are sort of disentangling or moving apart from one another, breaking some of those secondary bonds, those weaker bonds that hold adjacent chains together. And as a result, it decreases the stress that we observe in the material over time. Okay, and so we looked at different ways that we can model viscoelastic behavior using a spring and a dash pot. The spring is modeling instantaneous deformation. The dash pot, or the viscous element, is modeling deformation as a function of time, basically the viscous part of the response. And so this is the viscous part. This is the elastic response. If you put them together, you've got viscoelastic material. Okay. All right, so whoops. Skip that that review question. That should be in a different slide deck. We're going to do this review question though, talking about failure, since fatigue failure is something that we talked about during the last class. What is responsible for initiating failure, specifically in polymers? Okay, so we've talked about how the surface of polymers is important, and we've touched upon that idea, and we're going to come back to it often in this class. Characterizing the mechanical properties of biomaterials is a necessary thing to do, but even more important than the bulk properties of polymers are the surface properties. And one of the reasons is that small defects, scratches, little bubbles that formed in an injection molding machine that are incorporated into the final polymer form can be sort of nucleation sites, or sites where you can begin to get fatigue failure in polymers. So in fatigue failure, again, what we're talking about is cyclic loading and unloading of a polymer. This isn't just we apply a force once to the polymer. That's a tensile test. Fatigue testing, or fatigue failure in polymers, happens over time when we've loaded and unloaded the polymer many, many times. And we don't need to be at a super high tensile stress to do that, as we've talked about. Even if you're below the yield stress of the polymer, if you've got these little scratches or defects in the surface of your polymer, so here's your part. If you've got a little bubble, maybe from an injection molding process, or a crack, or even a little like scratch along the surface, you're applying a force to your material, some kind of stress here. Whatever stress you're applying to the material as a bulk is different than the stress that you would feel in this local region. The stress you would feel, or that the material would feel in the vicinity of a crack or a pore of some sort, is much higher than the bulk stress applied to the material. And so what happens is you get this crack widening over time. If you keep cycling the polymer, eventually this crack propagates all the way across, and the material would fracture, and the fracture pattern looks like a brittle fracture pattern of a brittle material. So it's kind of a clean break rather than a stretchy type of break that you would see from more ductile polymer applied with just a constant, a single stress applied. Okay, so most of you got that correct. That's great. Okay, just to rewind a little bit from where we were in the session on Monday, we started talking about building up our vocabulary around polymers. So polymers, the name comes, poly means many, and mer is the individual unit of a polymer. Mer is also called a monomer sometimes. Mono means one. So polyethylene, for example, has a monomer of, that's shown right here in red, 2 carbon atoms. So just a refresher, if it's been a while since you took organic chemistry, the points where these lines cross, there's a carbon atom here and a carbon atom here. And we leave those off the diagram for simplification, so it doesn't get too crowded. So this is what the polyethylene monomer looks like. Actually, if you had the monomer that was not polymerized, it would look like this, where you've got a carbon-carbon double bond. And we're going to talk about methods in a future class of how we actually polymerize these monomers to make these long chains. But usually a monomer will have a carbon-carbon double bond like this. So this is polyethylene. And polypropylene, the difference here is this methyl group on the polypropylene. So we're going to talk about these things a little bit later in class today, but just by looking at the molecular structure of a polymer, we can predict certain things about it, at least relative properties. We can predict the relative density of these polymers. We can predict the relative melting point of the polymers and their crystallinity just from looking at the structure. And what we want to think about when we're trying to predict those properties is not just one of these molecules, but if you had many molecules of polyethylene or many molecules of polypropylene, how well would those molecules be able to pack together with one another? Would they pack together tightly? Would they be more loose? And that property, how well the polymer chains can pack together, is going to predict some of those properties that I mentioned before. Okay, so we have this property called tacticity that we talk about with respect to polymers. Just because you make this is polypropylene, just because you make polypropylene doesn't mean you're going to get the same molecule all the time. Depending on the catalyst that you use and the conditions for the reaction, you can get different types of products. So here's an example of polypropylene. We can classify polypropylene as isotactic, syndiotactic, or atactic. And so if you recall these diagrams for organic chemistry, again, we've got a carbon at each of these little junctions on, this is called the backbone of the polymer chain, a carbon at each of these positions. And then these thicker molecules, these lines that go from thin to thick, mean that that is a bond that's coming out of the page toward us. It's meant to depict a 3D structure. And these dashed lines are lines that would go into the direction of the page. So these polymers, even though we draw them as lines, straight line structures, they are not, bonds are not at 90-degree angles like it is drawn here. It's more of a tetrahedral configuration, the sp3 bonding, if you remember that term from chemistry. And so, depending on the reaction conditions for making polypropylene, we can end up having all of these methyl groups on sort of the same side of our polymer chain. They can be in some kind of pattern where they're alternating on different sides of the chain, as you can see here. That's called syndiotactic, when there's some kind of alternation in the pendant groups. Or if it's just completely random, these pendant groups, there's no pattern to what side of the chain they end up on, we call that atactic. And so we've got 2 methyl groups on this side of the chain, and then 1 on the other, and then we come back to this side of the chain. There's no pattern in an atactic polypropylene configuration. So why do we care about this? Well, tacticity affects the ability of adjacent polypropylene chains to pack together tightly. Thus, it affects crystallinity, it affects density, and it can affect melting temperature, as you see down here. So if you look at this chart here in the bottom right corner, we see that isotactic polypropylene has the highest melting temperature of 3. Let's see if we can justify that looking at the structure. So in isotactic polypropylene, all of these bulky pendant groups end up on the same side of the molecule. So if you had many of these isotactic molecules next to each other, they can kind of pack close together because they have a predictable structure. There's not random appendages coming off on different sides. They might also form a helical pattern, like DNA does, for example, and coil. They can form various configurations like that. Syndiotactic polypropylene has a little bit lower so let me finish explaining isotactic. So isotactic has a high melting temperature because we have the closest packing of all three of these polypropylene molecules. Isotactic chains will pack together more closely than syndiotactic or atactic polypropylene. And the secondary, I don't even want to call them bonds, the secondary intermolecular forces between polymer chains will be strongest in isotactic polypropylene. So look at the other side of the spectrum. Atactic polypropylene has a melting temperature below 0 Celsius. And you can probably guess now why that is. If we've got these pendant groups associated on different sides of the chain in a random configuration, these molecules generally can't coil into a predictable pattern. They can't pack together as closely because you can see these bulky groups are just randomly shooting off the chain on one side or another. So because the molecules cannot pack as closely together, they don't have as many secondary bonds or intermolecular forces between polymer chains, like van der Waals bonds, dipole-dipole bonds, that sort of thing. They don't have as many of those, and what we see on the macro scale is that the melting temperature is lower for that configuration of polymer. Okay, some more vocabulary associated with polymers. We can have polymers that are of a single type, or we can have polymers, different types of polymers together, polymerized together in the same chain. So a homopolymer refers to one where all of the mers, or all of the individual units in the chain, are the same. So all of the polymers that we've seen so far in this class session are considered homopolymers. You've got a bunch of different monomers of polyethylene or polypropylene connected together. And there are some other examples here of different types of homopolymers that you might see. One of the most, I guess, famous copolymers, especially in BME, is something called PLGA, polylactic coglycolide. Polylactic, it's a polymer of lactic acid and glycolic acid together. And this is a degradable polymer. It degrades in the presence of water, and it has very friendly byproducts. One of the byproducts is water of the degradation. So this is one of the polymers that's used for degradable sutures, for instance, and for tissue engineering applications and drug delivery applications and all sorts of things, because it can degrade over time. And we'll talk about that much more later. But for the purpose of this lecture, PLGA is considered a copolymer because we've got two different types of monomers incorporated onto the chain. And you'll notice that there's an X here and a Y here. Those refer to sort of the ratio of lactic acid to glycolic acid that you have in your polymer. You can control that somewhat with the reaction conditions, but you'll want to characterize what this X and Y are, because they dictate the properties of the polymer. The methyl group on lactic acid makes lactic acid a more hydrophobic monomer than glycolic acid. So if you've got a PLGA configuration where the lactic acid content is very high, your polymer is going to be more hydrophobic than one where you would have a high glycolic acid component. So you can tune the hydrophobicity or hydrophilicity of your polymer by tuning the relative contribution or relative abundance of these two different monomers. Okay, so a homopolymer, all of the mers are the same, polyethylene or polypropylene, something like that. And then we can have copolymers where there are two or more different monomers polymerized together into the same molecule. And that can be done in different ways. It can be done randomly, as you can see here, where there's no pattern to the order in which the mers appear. We can have an alternating copolymer. So this would be lactic acid, glycolic acid, lactic acid, glycolic acid, and so forth. We can have what's called a block copolymer, where there's a string of one type of monomer and then a string of the different type of monomer together. Or we can even have what's called a graft copolymer, sort of like they graft a branch onto a tree or another type of plant, where the main chain consists of one type of polymer. It's a homopolymer of one chain, and we've grafted on a chain of a second type of monomer. So just some vocabulary to know when someone says, if your boss told you, for example, we need some PLGA copolymer for a project we're doing for some kind of device we want to make, you would need to clarify, well, do we need a random copolymer, alternating, or graft copolymer? There are different types of copolymers. So what type of PLGA would you want? And then for that matter, you would want to know what the ratio of L to G is that you would need for your product. So just developing some vocabulary around polymers that we're going to be using later in the semester. Okay, so a polymer molecule, a single polymer molecule is a long chain of monomers, as we've already discussed. But the bonds that connect the mers together are covalent bonds. These are the bonds that hold the backbone or the chain of the polymer together. And these are the bonds that hold these grafted or these branches together as well. Adjacent polymer molecules. So if you've got more than one polymer molecule, because you always have more than one polymer molecule, those are not held together, typically are not held together by primary bonds. They're typically held together by secondary bonds, such as the ones that you see here. So in a linear or branched polymer, we have covalent bonds holding the backbone chain together. The forces between chains in a linear or a branched polymer, such as a hydrogen bond or a dipole-dipole bond, those are secondary bonds, and those are weaker than the covalent bonds holding the backbone together. So if we heat up these polymers, or if we apply a stress to these polymers in this direction, these chains can start to slide past one another with relatively little force applied, because it doesn't take that much force to break these secondary bonds and allow these spaghetti noodles to slide past one another. However, we can also have polymers that are cross-linked or even networked. And in these two configurations, cross-linked and networked, the bonds between chains are primary bonds. They're covalent bonds. Now, what's the difference between a cross-linked and a networked polymer? Generally, cross-linked polymer is going to look like a linear polymer with just some ladder rungs, basically connecting adjacent polymer molecules. But you've got single connection points here, connecting one chain to another. In a networked polymer, each molecule or many of the molecules will have more than two bonds. So you can see this guy's got 3 bonds. This guy's got 3 bonds. It's bonded to many, one chain is bonded to many other chains together. So if you think about what the mechanical properties of these two might be like, we're probably gonna have to put in some more effort to move these cross-linked chains past one another, right? Because now we have to break primary bonds rather than just secondary bonds. Primary bonds are stronger. We have to put in more energy to break these. As a result, we're going to see a higher tensile strength in cross-linked polymers, higher still in networked polymers, and you might have you might be able to apply force from different directions and have a higher tensile strength in different directions in a networked polymer than in a cross-linked polymer, for instance. Okay. So I may have already answered this question inadvertently, but just a quick clicker poll here. Which of these polymers would you expect to have a higher ultimate tensile strength? Okay, whoops. Oops, trying to view the poll. Excellent. Okay, most of you answered B, which is correct. And so why is that the case? Well, there are associations between the chains in a linear polymer, but the associations are secondary bonds. So that would be hydrogen bonds, dipole-dipole bonds, and so forth. Versus in a cross-linked polymer, the bonds between chains are primary bonds, which are stronger. So if we've got stronger bonds between the chains, that means we're going to have to put in more energy to move those chains and slide them past one another. So cross-linked polymer would have a higher ultimate tensile strength. Okay, whoops. And in a previous class session, we talked about how the behavior of polymers, specifically their mechanical properties, are temperature dependent. Really, the properties of all materials are temperature dependent, metals and ceramics included, although you generally have to heat metals and ceramics to a much higher temperature to see the type of behavior that we are going to see here. But the other difference between metals and ceramics and polymers that metals and ceramics typically have a crystalline structure, a repeating network structure. The metallic bonds that we talked about before, the ionic bonds, we have some kind of ordered network. Polymers can be configured in a number of different ways, as we've just discussed, and consequently, we can classify polymers as either being crystalline, which we'll talk about more in a bit, amorphous, or in other words, not crystalline, or semi-crystalline. And depending on how crystalline or not a polymer is, we use different characteristic temperatures to describe what's going on in that polymer as we change its temperature. Okay, so we start at a low temperature over here, and we have a high, relatively high stiffness, or relatively high Young's modulus of the material, put E up here. As we heat up the polymer, the stiffness is going to decrease. As you can imagine, it gets more rubbery and starts to give a little bit. If we've got a crystalline material, like a metal or ceramic, we heat up that material for a long time, and the stiffness remains the same until a certain point, which we call the melting temperature. The curve takes a rapid downturn. We rapidly lose stiffness as our material starts to melt. It turns from a solid into a liquid. So for a semi-crystalline material, again, this is not just polymers, but metals and ceramics are crystalline as well. We describe a melting temperature for those materials. If you've got a material that's amorphous, as many polymers are, you can talk about a melting temperature there. So this would probably be the melting temperature of the amorphous polymer. But we also talk about a temperature that is characteristic of, tells us what's going on in the material. We talk about a glass transition temperature, which is shown up here on the plot. The glass transition temperature signifies the point in an amorphous material where the stiffness, or the Young's modulus, takes a rapid downturn. What does that mean physically, what's going on in the molecule? At the glass transition temperature, an amorphous polymer has sort of got enough energy to start to give and to start to move. Those chains can start to slide past one another, and we get some deformation occurring in the polymer. Another way to think about what's happening on the molecular scale is that at the glass transition temperature, the bonds in the polymer chain have enough energy to be able to rotate. So once they rotate, that means they've broken their secondary bond associations with other adjacent polymer molecules. We start to get some movement. They can rearrange themselves, as it says down here. The adjacent polymer molecules can start to slide past one another. So the summary here is that we've got two different characteristic temperatures for polymers. We can talk about a melting temperature for materials that are crystalline or semi-crystalline. And for amorphous materials, we generally use, instead of melting temperature, we generally talk about the glass transition temperature as the temperature at which interesting things start to happen in the polymer, meaning that it starts to deform, bonds start to rotate, and the chains start to slide past one another. And it rapidly loses stiffness as well. You can talk about melting temperature for an amorphous polymer as well, but you generally don't talk about a glass transition temperature for crystalline materials. Generally only used for, crystalline materials, we only talk about the melting temperature with those. Okay, so what is all of this talk good for? Well, again, we're able to sort of predict some of our properties of our polymers just by looking at the molecular structures and knowing that as temperature increases, what's happening in our polymer. So as you increase the temperature in a sample of polymer, you're adding energy to the polymer. You are giving that polymer almost permission, you're giving it the ability to start to rotate bonds. You're breaking secondary bonds between polymer chains. And so then those pendant groups in the backbone of the polymer itself can start to rotate. So ultimately, good property to predict the glass transition temperature, we want to think about how readily the bonds of a polymer backbone can rotate. So I've got three examples here. We've got polyethylene monomer, polydimethyl siloxane monomer, and a polypropylene monomer. So looking at these three structures, you can think about which of these three structures, we're talking about this bond right here, either the carbon-carbon or the silicon-oxygen bond, which of these three bonds would be the easiest bond to rotate in your mind? Now, I'm not going to stop here. I'm going to keep going because I want to get through some of the material today. But the polydimethyl siloxane monomer is going to rotate the most easily. Why is that the case? How did I know that? Well, there's nothing, there are no other atoms connected to this oxygen here. So there's no bulk to interfere with rotation around this silicon oxygen bond. So the next highest glass transition temperature would probably be polyethylene here, because we do have hydrogens bonded to these carbons, but hydrogen is the smallest atom that you can have. So this is sort of minimal hindrance to rotation around this bond. The highest glass transition temperature of these three monomers would be polypropylene because of the presence of this guy right here. This methyl group is a relatively bulky group compared to having just a hydrogen there. And so rotation around this bond is going to be a little bit more difficult because of this bulky guy hanging out here. If you remember the concept from organic chemistry, or even from regular chemistry, of steric hindrance, that's what we're talking about here. So to predict glass transition temperature, looking at monomers, you want to think about how bulky these side groups are. And you can also think about the polarity of the side groups or of the chains. Let me advance the slide here. Okay, so our lowest glass transition temperature is PDMS, as we predicted. The second lowest glass transition temperature is polyethylene because we've got relatively little steric hindrance. And then the highest glass transition temperature, the polymer that needs the most energy input to begin rotating, is polypropylene because of this steric hindrance of this group right here. The other thing to think about in addition to steric hindrance is the polarity of the chains, the readiness with which they can form bonds between polymer chains. So these are both secondary bonds. We're talking about the bonds between polymer chains here. The better monomers or the better polymers are able to make these secondary bonds, the higher the melting temperature for that material. So, next slide. Okay, so again, we've got these two temperatures, characteristic temperatures for polymers. The melting temperature is associated with crystalline or semi-crystalline polymers. Glass transition temperature is typically associated with amorphous polymers. And we've talked about a number of factors that can influence the glass transition temperature, or that can allow us to predict the relative glass transition temperature of the polymer. We've got three different factors here. So let's discuss quickly, how would the molecular weight of the polymer affect the glass transition temperature? What do you guys think would be the trend there? Or the relationship between molecular weight and glass transition temperature?
So it needs to transfer from glass to rubber in order for the rubber to melt.
Uh-huh.
And also to ask, so how come amorphous metals cannot melt easily? Because I thought that salt melts at a lower point when it's amorphous than crystal due to the structure.
Right. So what do you mean by easily? So
How come
amorphous metal
only applies to crystalline but not amorphous?
So amorphous metals should melt at a lower temperature than crystalline metals. But we don't really associate a glass transition temperature with metals.
Yeah, I wasn't asking about metals. I was talking about melting temperature can be observed in crystalline substances.
Yes.
But it can't be observed in amorphous substances. Why is it like that?
It is observed, but the melting temperature in amorphous substances, after the melting temperature, the polymer pretty much turns to goo. It's kind of, it's not very useful as what we would think of to use a polymer for at that point. So when we're thinking about temperatures to use for forming the materials, like for manufacturing, glass transition temperature is generally what you want to keep an eye on and plan your process around, rather than a melting temperature. You can definitely, they do tabulate melting temperatures for amorphous polymers, but we use glass transition temperature. It's much more useful characteristic or property of the polymer. Did I answer your question?
Yeah, thanks.
Sure. Okay, so I'll go ahead and go through these factors. So the molecular weight of the polymer. You can imagine, we talked about what dictates the ability to predict the glass transition temperature. We're talking about the ability of molecules to rotate in the backbone of a carbon chain, for example. In order for bonds to be able to rotate around the backbone of a polymer chain, so if we want to rotate this bond, for example, you have to break associations, secondary bonds, between this chain and an adjacent one. The longer your polymer is, so the higher the molecular weight of your polymer, the longer the polymer is, the more of these secondary associations you are going to form. So the longer your polymer is, the higher the molecular weight, the higher the glass transition temperature, because the more you're going to need more energy to be able to break more bonds in the material. So molecular weight influences glass transition temperature. If you've got very bulky functional groups, that's actually going to decrease your glass transition temperature, as we saw on the last slide, because you're not going to be able to form this close of packing of your polymer chains together. You're not going to be able to form as many secondary bonds between the chains. So the bulkier the functional, in general, the bulkier your functional groups, the lower your glass transition temperature of the polymer. And then finally, this is probably the easiest one to predict the relationship. If you've got cross-linking in your polymer, the more cross-links you have, so the more primary bonds you have between polymer molecules, the higher your glass transition temperature, because the more cross-links you have, the more energy you will need to input to break those bonds and have the polymer chains move past one another. Okay, so we can predict properties, macro scale properties of polymers just by looking at their chemical structure, which I think is pretty cool. Okay, so we can describe polymers as either crystalline, semi-crystalline, or amorphous, and we can associate different characteristic temperatures with each of those. And what we have when we form crystals, this is kind of what they look like. I've got an image over here on the right. If you've got a predictable, repeatable pattern in your polymer backbone, the polymer can sort of fold back on itself, like you see right here. The polymer is folding back on itself and forming these domains. If you get many of these domains together, they can form these they kind of look like a starburst-like structure called a spherulite. So this little image here, this is called a spherulite. And most often polymers are not 100% crystalline. Most of the time we would classify polymers as semi-crystalline because in order to have these different regions of order, there are little regions in between the regions of order that are amorphous. So this spherulite here is considered a semi-crystalline structure. These areas of regular predictable order are the crystalline domains or crystalline regions, and these areas in between them with little loose flyaway hairs or spaghetti strands are amorphous regions. So the closer, what dictates the formation of a spherulite, the closer we can pack polymer chains together. So the fewer bulky side groups there are, the more secondary bonds we could have between our chains, the closer those chains are going to be able to pack to one another. The closer the chains can pack together, the more of these structures, lamellae, you will form. This is a lamellae, means like layers. And the more lamellae you form, the more likely you are to form a spherulite and have crystalline domains in your polymer. So the degree of crystallinity, or the percent, we can talk about a percent crystallinity, you can quantify that by taking experimental measurements, depends on how many branches you have off of the backbone of your polymer, or the bulky functional groups or pendant groups off of the backbone of your polymer, the length of the chain or molecular weight related to chain length, and the degree of cross-linking you have in your polymer. And so as a last activity today, I have a couple more clicker questions. Here we have a table showing some properties of polyethylene. And as we talked about at the beginning of today, you can have polyethylene, it's still considered polyethylene. You can have it in a number of different configurations. We have different densities of polyethylene. So LDPE is a low density. Where's my pen? Oh, well. LDPE is a low density, MDPE is a medium density, and then high density and ultra high molecular weight polyethylene is what we have here at the bottom. This stands for ultra high molecular weight polyethylene. We're given the structure of each polyethylene, and we're given the density of each polyethylene. And I'm asking you here to predict which of these two would you predict has a higher percent crystallinity? LDPE, right here, LDPE, I just gave away the answer. LDPE or LLDPE? This one or this one? Or A or B, I guess I should say. Okay. Clicker's giving me issues today. It's always something. Okay, most of you answered B, which is correct. So let me advance the slide. Okay, and why would LLDPE have a higher percent crystallinity? Well, the things that we know about the polymer are the density and the structure. So if we look at the density, LLDPE is denser. Increased density means that we've got closer packing of our molecules together. If molecules can pack closer together, they tend to make these lamellae, which can make spherulites, and that's what we mean when we talk about crystallinity, the presence of those spherulites. Okay, so question number 2, now looking at the next two in the chart, which of these has a, well, not the next two, these two, which of these two has a higher percent crystallinity? You guys are correct. Most of you answered B here. And why would we answer B? Well, again, actually the density of these two is considered the same. But if you look at the structure here, this one, they both have lamellae. So we'll go on to looking at the molecular weight of the polymers. Molecular weight of LLDPE is very low compared to the molecular weight of the ultra high molecular weight polyethylene. And we know that molecular weight is a predictor of glass transition temperature. It's also a predictor of crystallinity. Higher the molecular weight, the more order we can form between polymers. And so if I advance the slide. Okay, we'll skip the last question because we're out of time for today. But the ultra high molecular weight polyethylene has a higher crystallinity than the LLDPE because we don't have as much branching in that polymer. So we can tell a lot about the polymer's macro scale characteristics just by looking at the structure, molecular connectivity of a molecule. And that's what we're calling the structure function relationship here. So be looking, as you're doing your research for your term paper, be looking of ways that you can connect the structure and function in the polymers that you are looking at for your medical device.